Friends, we continue with the study of voltage stability. Today we shall study the determination of shortest distance to instability, the continuation power flow analysis, and at the end we will study the techniques which can be used to prevent the voltage collapse or voltage instability. Now, let us try to understand briefly what we mean by the shortest distance to instability. The purpose of this study is to determine the smallest stability margin, that is, whenever you are operating at a certain loading condition, then we would like to know that how much increase in load can be made so that the system becomes unstable. It means how far we are from the instability, but our interest is to find out the shortest distance. In fact, actually suppose you are operating with a certain loading condition, then the load can vary in a variety of manners, right. Then for each particular combination of loading, if you stretch the load in a particular direction, then you will reach a one particular point where the system becomes unstable. We want to know what is the direction in which when we stretch the loading, so that the instability occurs with a minimum distance. Now, to understand this basic point, we consider here a simple radial system. In this radial system, you have one source, one transmission line, and say let us say the load here, we will call it P. I am considering the simplest system, but any multi-machine system, a large system, there are several loads connected at various buses, and therefore, whenever you want to can say increase the loading can be increased in a variety of manners, right. But we know actually that when you increase the load at a one particular loading condition, the system becomes voltage instability occurs, or system becomes voltage unstable, and at that loading condition, if you find out the Jacobian of the matrix, then that Jacobian becomes singular, right. Now, here for this simple radial system, we plot here actually in the PQ plane, this is the load reactive, this is the load in per unit, that is the active power P. On this side is the reactive power, that is you put P on this side, P here, and the reactive power Q on this axis. Now, we can find out one surface, if you any point on that surface will lead to, if you operate at that point, then it will lead to voltage instability. In case it is a large system with number of buses, right, that surface comes out to be a hypersurface, right. And in this particular case, in a simple radial system, right, we get actually a curve, right. Now, this is the curve. Now, suppose you are operating initially at this point called POQO, the initial loading condition is denoted as POQO, and suppose you increase the load P and Q at random. Let us say you increase in this direction, so that you come and reach the surface S, or actually the curve S, This is called the surface S or curve S, right. Now, at this point the system becomes unstable. Now, suppose now the question is actually that what is the shortest distance to instability. To find out the shortest distance, obviously in this particular case the shortest distance one can find out. First you find out the normal at this point 1 to the surface. Let us call this is the normal at this point, call it say eta 1. Then again go back to the initial loading condition and stretch the load in parallel or in the direction of this normal. That is, second time when you are stretching in this direction, this is parallel to this. You reach this point 2. Then once you reach the point 2, again you find out the normal at this point eta 2, and then again go back to the initial condition and stretch the loading in the direction parallel to the normal. Then you will land to a point where the distance between the initial operating condition and the new operating condition will be minimum. That is, one can find out, suppose you represent actually the initial operating condition by a vector rho, a parameter vector rho. Now, this parameter vector rho is the initial operating condition, and let us say rho psi is the final operating condition. Then our interest is to find out this distance, that is the rho psi minus rho naught, norm of this quantity. This should be minimum, right. And for a simple 2 machine system, not 2 machine systems, for a simple radial system, I have illustrated that you start from initial condition, stretch the loading in any direction. Here P is increasing while Q is decreasing, like that, and you reach to a new point. Then at this point 1, since this point 1 lies on the surface, which is the which represent the unstable operating condition, then the normal which you find out at this point, right. Now, you stretch in the direction of the normal, and therefore you keep on doing this till you get the minimum distance. Therefore, in the multi machine system we denote actually the loading condition in terms of initial P and Q through a parameter, and we find out the final as rho star. And in case the rho star is such a loading condition, so that the moment you are operating, this rho star lies on the hypersurface, which represents the unstable operating condition, and that our objective is to find out the norm of this quantity, that is rho naught minus rho star minus rho naught, norm of this quantity, and this should be minimum. And this process is documented in various papers, how to find out for a multi machine or large system this norm. The purpose of this obtaining the shortest distance is to know that at what stability margin we are operating, because whenever you are operating system, you would like to maintain certain stability margin all the time. The next point we will study is the continuation power flow analysis. The continuation power flow analysis is very important and is a very important tool which has been developed for obtaining the critical operating condition. In fact, as we know that if you operate near the critical point or at the critical point, then the Jacobian becomes singular. That is, the Jacobian matrix becomes singular at the voltage stability limit. Consequently, the conventional power flow algorithms are prone to convergence problems. That is, the moment the Jacobian becomes singular, right, the convergence problems arises. And therefore, if you try to plot actually the we call PV curve, right, then we will be in a position to get certain points on the PV curve by conventional load flow analysis, but the moment you reach closer to the instability point, you will find Jacobian becomes singular. But to solve this problem, the continuous power flow algorithm has been developed. That is, the continuous power flow analysis overcomes this problem by reformulating the power flow equations, so that they remain well conditioned at all possible loading conditions. This allows the solution of power flow problem for stable as well as unstable equilibrium points. That is, when you look at the PV curve, right, then the upper portion of this PV curve represent the stable operating points or stable equilibrium points, but the lower portion, right, they are the unstable. Now, these points one we cannot compute or we cannot get by conventional power flow equations or conventional power flow algorithm. Now, this continuation power flow approach has been well documented, and the most important research paper where this continuation power flow has been discussed is written by V. Ajarappu and C. Christie, the continuous power flow, the continuation power flow, a tool for steady state voltage stability analysis. IEEE PICA conference proceedings, page numbers 304 to 311. It appeared in May 1991. This is a very standard reference paper for understanding the continuation power flow algorithm. We will briefly study the salient features of this continuation power flow algorithm. Basic principle: the continuation power flow analysis uses iterative process involving predictor and corrector steps, as we will discuss just now. That is, the basic principle in this continuation power flow is that there are two steps. First is, suppose you are operating at an initial point, first we find out through the predictor step, right, and then from that predictor step we go to the corrector step. There are two steps involved, and these steps are followed iteratively to get the solution. To understand this basic concept, let us look at this graph. This graph shows actually the load on this axis and the bus voltage on this axis. Now, this is the PV curve which is plotted or part of it can be plotted by repeated application of load flow analysis, right. Now, suppose we are operating at this initial operating condition at A. The first step will be we find out at this operating condition A tangent vector, that is, there is a tangent vector which we find out. For example, this is the tangent vector at this operating condition. Then the next step is, once we find out the tangent vector, we want to find out what is the step length. Therefore, the step length, for example, in this case shown is A to B. Therefore, the step length is also a important decision to be taken. Now, once you come to this point B, next step is at this, from this point we come to the actual solution C, that is called corrector step, from B to C. That is, at this, if you see here actually that this graph, which is the firm graph, that shows the actual solution. This is the exact solution. This graph shows the exact solution. I will just draw it with a different color to make it more clear. That is, this blue graph which I have shown here is the exact solution. That is, we want to come from A to C, but how do we come from A to C? The step is, at A you find out a tangent vector, then you select judiciously the step length, then from this point B is not on the solution, exact solution. At point B you apply corrector step and come to point C, right. Now, this approach is to be applied to find out the solution for different points on this graph. Here it is possible to get solution, so that we can get the critical point. For example, this is the critical point, and then we can get points which are below the critical point also. That is the complete part of the complete, you can say, PV curve can be obtained for a particular bus in the multi-machine system. Now, let us study actually the algorithm, the mathematical formulation. The basic equations are similar to standard power flow analysis, except that the increase in load is added as a parameter. Generally, in a conventional power flow, what we really do is that the loads are known to us and we solve the problem. Now, here what we do is that increase in load is added as a parameter, that is increase in load is added as a parameter. This is one difference here. The reformulated power flow equations with provision of increasing generations as the load is increased may be expressed as. Now, the point here is that any system, when I increase the load, right, then I may have to increase the generations also, right, so that the load generation match is achieved, right. Therefore, whenever you increase the load in a particular fashion, then you have to increase the generations also. That is what it writes here is, you reformulate the power flow equations with provision of increasing generations as the load is increased. The load flow equations can be formulated in this fashion: f theta v equal to lambda times k, where f is a nonlinear function of theta and v. It means f theta v is represents actually f theta v equal to lambda k, it represents the set of nonlinear algebraic equations. Okay. Here f is a function, in fact general f is a function, and this equation is actually a vector equation. A large number of equations are there, a vector equation. Here lambda is called the load parameter, theta is the vector of bus voltage angles, v is the vector of bus voltage magnitudes, and k is the vector representing percent load change at each bus. That is, k is the vector representing percent load change at each bus. In fact, here when you look at the equations, what we find here is that is lambda into k. We can fix actually some percent load change and multiply by a parameter lambda. The magnitude of lambda varies from 0 to some critical value, right. It means the amount of load change which we put here is adjustable. The above set of nonlinear equations is solved by specifying a value for lambda such that lambda is between 0 and lambda critical. When lambda 0 stands for base load condition, when lambda equal to 0, it means we are not giving any increment in the loading condition, and lambda equal to lambda critical represents the critical load. That is, if the value of lambda is equal to lambda critical, then we have reached the critical loading condition. The equations which we have put here, that is the equations which we are put as f of theta v equal to lambda k, right. This equation can be reformulated or rearranged in the form f theta v lambda equal to 0, k is a constant, lambda is a variable parameter, right. They are the set of nonlinear algebraic equations. Now, here to apply the continuation load flow algorithm, as I have discussed, there are two steps. One is called predictor step, another is called corrector step. First, let us examine the predictor step. once a base solution has been found, that is lambda equal to 0, a prediction of the next solution can be made by taking an appropriately sized step in the direction tangent to the solution path. That is, our interest is to find out actually the predictor step, that is to find out next solution. To find out next solution, a prediction of the next solution can be made, it is a prediction, by taking an appropriate sized step in the direction tangent to the solution path. That is, we start from the initial condition, find out the tangent, that is the direction. Thus, the first task in predictor process is to calculate the tangent vector. That is the what we have discussed here, the tangent vector is very important, and therefore, in the predictor step, the step is how to calculate the tangent vector. The approach is very straightforward. We obtain the differential of this equation, that is d of f theta v lambda. This function can be written as f naught d theta plus f v dv plus f lambda d lambda. This is equal to 0. Now, here this f theta, f v and f lambda, these are the matrices of partial derivatives, and this equation can be arranged in this form: f theta, f v, f lambda, that is these matrices of partial derivatives are arranged and make into this vector d theta, dv, d lambda equal to 0. Since actually we have theta, the dimension of theta is equal to number of buses in the system, right. Similarly, or you can say actually d theta and dv, right, these are n vectors, and lambda is of course one scalar quantity. Therefore, this vector d theta, dv and d lambda, this vector is given the name tangent vector. That is, tangent vector is defined as d theta, dv, d lambda. Our interest is to find out this tangent vector. To find out the tangent vector, we have just now seen what we really do here is this equation. But now the question is how to solve this problem. Now, if you look here, so far the partial derivatives are concerned, right. This, there are the number of unknowns I have now increased by 1, lambda is the additional parameter which we have added, and therefore, there is a necessity to add one more equation here, so that you can solve this for this tangent vector. That is, one of the components of tangent vector is set equal to plus 1 or minus 1. That is, the first our step is how to solve this problem, how to get the tangent vector, right. Therefore, the approach is that first we add a row vector Ek to the set of differential equations or to this Jacobian matrix Ek. This vector Ek, except the kth element, all other elements are 0, is a row vector, and our interest is that we want to make one of the component of the tangent vector equal to plus 1 or minus 1. So, that when this row vector accept one quantity, others are all 0. So, that when you multiply this, you will find actually that the delta lambda will come out to be equal to plus 1. That is, here we are making actually this Ek in such a fashion, so that you get d lambda, one of the elements of the tangent vector equal to 1. For example, if you want to make one of the elements of voltage component, right, that is, say, let us say the voltage of bus 1 dV1 or dV2, any one, or similarly phase angle of any of the bus voltages. That is, in this you can make one of the elements equal to 1. You make plus 1 or minus 1. Plus 1 is corresponding when you are operating on the upper part of the PV curve, and minus 1 when you are operating on the lower part, right. So, that in this reformulated equation, we have now we have now a situation where we can compute this tangent vector. Okay. Now, this imposes a non-zero norm on the tangent vector. The idea is that by this approach, by adding this row vector E k and making one of the elements as plus minus 1, right, what we have achieved is that two things which we have achieved. First thing is that this row vector, right, it becomes a non-zero norm tangent vector. That if you find the norm of this tangent vector, then it will come out to be non-zero, it will not become 0, right. Second is guarantees the augmented Jacobian will be non-singular, that is the Jacobian which we have augmented now, this Jacobian becomes non-singular, and you can find out the tangent vector. That is, one tangent vector is found once tangent vector is found, the prediction of the next solution is as follows. That is, what we really do is that we first compute the tangent vector, and the moment you compute the tangent vector, the new tangent vector is obtained as theta, not tangent vector, this is the tangent vector d theta, dv and d lambda, this is tangent vector. The new operating condition, that is theta, v and lambda, obtained as the initial values of this vector plus sigma times the tangent vector. This sigma is the step length, sigma is the step length, step size. Okay. The step size sigma is chosen so that the power flow solution exists with a specified continuation parameter. And the idea here is that the step size sigma should be such that now you can perform the normal power flow solution and obtain the complete solution, that is, you can find out all the voltages and their phase angles. I will just generally you will find actually that in case suppose the step size is large, then from that predicted solution you will not be in a position to get the corrected, that is actually the load power flow solution when you try to perform, right, the solution will not give actually this the exact solution of the required solution. In that case we reduce the value of sigma, again repeat till we find out actually that in the corrected step we get the solution. If for a given step size a solution cannot be found in the corrected step, the step size is reduced and the corrected step is repeated until a successful solution is attained. This is actually very important, that what should, because we do not know what should be the corrected size, what should be the step size. Suppose you take a very small step size, then you will require large number of iterations. If you take a large step size, it will not converge, right. Therefore, one has to take very judiciously the step size. Next step is the corrector step. The corrector step is, idea of the corrector step is to really perform actually the load flow and get the solution. Now, again if you see here actually this function f theta v lambda, right, the number of unknowns are theta v and lambda, right, but the number of equations will be one equation less, because when you have formulated the number of equations, you have added a term lambda into k, but number of equations were still the same. Now, to get the solution, what is to be done is we add one more equation. This equation is written as x k minus eta equal to 0. That this x k, this is very important point here, the x k is the state variable selected as continuation parameter. What are the state variables? All the phase angles, all the bus voltages, right, and lambda. they are the state variables here, right. And therefore, what we do is that xk is one of the state variables and this is chosen as a continuation parameter, and the eta stands for value of xk, that is the predicted value of xk, because xk is one of the state variables, right. And therefore, if you look here with our process, then we start from the initial operating condition, then we find out the tangent vector, and suppose you start from point A and go to B, B is the predicted solution. Therefore, at this B we know all the values of we know the value of the complete state vector, right. And therefore, xk is the continuation parameter which is chosen and it is one of the state variables, and value of xk is chosen equal to lambda, which is the predicted value of xk, predicted value of continuation parameter. Therefore, the number of equations which now we have will be one more additional equation you have added, and therefore, this set of equations can be solved by a normal load flow, and you will get the solution. This is what is called corrector step. Now, the question basically is that how to solve this problem, how to choose actually the continuation parameter or continuation variable, the xk, then because xk is one of the state variables to be chosen as a continuation parameter. The tangent component of lambda, d lambda, is positive for the upper portion of the Vp curve, 0 for the critical point and negative for the lower points. Okay, we have already mentioned. The question is how to select the continuation parameters, right. Obviously, one can choose any one of the state variables as continuation parameter, but for optimum solution the approach is, a good practice is to choose the continuation parameter as the state variable that has the greatest rate of change. In fact, what we do is that we find out the tangent vector, and in this tangent vector the element which has the highest value is chosen, corresponding to that is chosen as the continuation parameter, or that state variable which has the highest or greatest rate of change is chosen as the continuation parameter. Let us look at the flow chart of this continuation power flow algorithm. The flow chart is, as usual, you start your problem. First step is run the conventional power flow on base case, run the conventional power flow and on the base case and find out actually the initial solution. Specify continuation parameter. Now, here at this stage, how to specify the continuation parameter? We have not calculated the tangent vector, and therefore, the suggestion is you can choose lambda itself, which is the load parameter, as a continuation parameter, right. The next step is calculate tangent vector, for which the equation has already been specified, that is, you calculate the tangent vector. Next is, if critical point has been reached, that is, you have to check whether you have reached the critical point or not. If you have reached the critical point, you stop there. Otherwise, choose continuation parameter for next step. The first step, the continuation parameter was chosen arbitrarily, and I told you that we can choose the load parameter as the continuation parameter. But here, now once you have this tangent vector, we can choose the continuation parameter. Then after choosing this continuation parameter, predict the solution. After this prediction, you go for the correction, that is perform the correction part and then return back to this point again. And this process continues till you reach the critical point, and you can go below the critical point also and get the other points operation. This is a very important algorithm which we have discussed just now. Now, the problem here is that should we use the continuation load flow algorithm right from beginning, or should we use it actually when we reach the near the critical point? The answer is obviously you first solve this continuation solve this problem by normal conventional load flow. That you are operating at initial condition, you give increment in load, again perform the load flow analysis, find out the new solution, and till you come very close to the critical point, you can keep on using the conventional load flow. But the moment you reach the critical point or near the critical point, the Jacobian becomes at critical point becomes singular, and therefore, before or closer to the critical point, you can now resort to the continuation load flow algorithm and obtain the points, operating points, which are the critical operating points. The idea here is that the continuation load flow algorithm, it takes more time to get the solution, because it has two important steps, the predictor and corrector steps. And so far the conventional load flow is concerned, you can increase the load in a particular direction and find out the solution. Next point we will discuss is what can be done and how the system can be designed and operated so that we avoid the voltage collapse situation. That is, we want to operate the system so that we can prevent the voltage collapse. Now, here we will divide this our discussion into two different headings. One is the system design measures, that is, when you design the system, you take care so that it has a inherent stability margin, right. And then next is operating measure, that is, when your system is already there, how to operate the system so that the voltage collapse is avoided. System design measures. What are the design measures which can be adopted for having a system which will have a large voltage stability margin and voltage collapse would not take place? Obviously, when we have discussed this voltage stability problem, the voltage stability problem is basically the problem of inadequate reactive power supply. It is a situation where the system has less reactive power supply capability, it cannot supply the required amount of reactive power and the voltage collapse takes place. Therefore, obviously, the first solution or first design approach should be, design measure should be, apply reactive power compensating devices or adequate reactive power compensating devices. Apply. We should have various sources of reactive power, and that these reactive power sources should be applied very judiciously. We will discuss this application part in the next step. Second will be control the network voltage and generator reactive power output. That is when the system is under the design stage, design measure itself, right. You provide certain controls which can be used for controlling the network voltage and the generator reactive power output. Then you should have the control so that you can increase or decrease the reactive power output from the generating devices. Then there may be certain protections and controls you should have proper coordination. Sometimes the protection that was when you are controlling a load, let us say, right, and one arrangement is that whenever the voltage is decreasing, you can do load shedding and voltage will recover. Therefore, load shedding is one of the controls, and therefore, whatsoever protection and control devices you incorporate in the system, load control devices or voltage control devices, all should be properly have proper coordination with the protection systems. Then also have proper control of the transformer tape changes. They are the voltage control devices, you have to provide certain arrangements so that you can control actually the control the tape changer positions. Then next is under voltage load shedding. If there is a last resort, in case you find that voltage is sinking, voltage is going low, you do the load shedding. For example, under frequency load shedding, all of you know, right, when the system frequency is going down, we do load shedding so that the frequency is recovered, right. Similarly, when the voltage is low, one can resort to what is called under voltage load shedding, but this should be done very judiciously, and this should be considered a last resort for saving the system from voltage collapse. Right. Therefore, the point is that these measures which I have put here, they are the design measures, and therefore, you should have a provision in the system, so that you have a provision of under voltage load shedding as a built up strategy to avoid voltage collapse phenomena or voltage instability phenomena. In case suppose this provision is not exist, it will not work, right, and generally you will find that the human intervention may sometimes be successful, but may not be successful. But here when I talk about this is a automatic under voltage load shedding scheme. Now, let us discuss these things in slightly more detail. Application of reactive power compensating devices. We know that we have the various reactive power sources. Our interest here is that you should design your system so that you have adequate stability margin. That is when you plan for the reactive power sources, you plan in such a fashion so that you have adequate voltage stability margin by proper selection of compensating devices. In fact, here the selection of sizes, what should be the size of the compensating devices, what should be the ratings, what should be the locations, all these things should be done by a detailed system study covering the most onerous system condition for which the system is required to operate satisfactorily. Idea here is that when you are doing this design, you have to can say determine what should be the location of the reactive power sources, what should be their sizes, and what should be the type, in the sense that it is controlled or is fixed, or whether there should be continuously controlled or whether it should be discrete control. That the idea here is that when you write at the design stage, you have to perform a detailed system study or detailed system optimization studies have to be done, so that you find out actually the sizes, locations, type of devices, and that should all include the most onerous or most actually the most heavily loaded condition, right. We want that at that condition system should be stable. Third is design criteria on maximum allowable voltage drop following a contingency are not often satisfactory from voltage stability point of view. Sometimes whenever we design the application of reactive power sources, the one approach will be that okay, suppose a certain contingency occurs, right, what is the maximum permissible voltage drop, and based upon that you design the reactive power sources. But the suggestion is that instead of going for this type of situation, one should design from the point of view of stability margin. That is, the stability margin should be based on megawatt and MVR distances to instability. That is, how much real power and reactive power increment can be put on the system, right, till instability occurs. That is what is the point. Actually, I have already discussed the minimum distance to instability. Therefore, the criteria should be we must design our system so that there is a minimum inbuilt voltage instability. Next is control of network voltage and generator reactive power output. Again the design step. Now, here so far actually the reactive power sources are concerned, the generator is one of the most important reactive power source, and the generators have automatic voltage regulators. One way is that you regulate the voltage at the terminal of the generator. Another way is that using load compensators, you regulate the voltage at a point away from the generator terminal. That is, the point which you choose for regulation may be not the terminal voltage of the generator. Suppose this is generator, this is the step up transformer. That is, you can regulate actually the field current of the generator through AVR, so that you maintain the voltage on the high voltage side of this transformer constant. This is normally done with the help of load compensation devices, or load compensators are provided to take care of this. The AVR regulates the voltage on the high tension side of or part away through the step up transformer. You can always regulate so that some voltage may not be at this point, may not be at this point, but in between. That is what one has to decide. That is, the load compensation of the generator AVR regulate the voltage on the high tension side or part away through the step up transformer. This has beneficial effect on voltage stability by moving the point of constant voltage electrically closer to the loads. In the sense that what is happening, that this constant voltage point is now coming closer to the loads. Right? This is one approach, that instead of regulating the terminal voltage, you regulate a voltage at some other point using the AVR, load compensation devices. Then many utilities are developing secondary control or secondary voltage control schemes for centrally controlling voltages and generator reactive power output. In the sense that instead of actually having the decentralized voltage control, you can take the system as a whole, right, and monitor the system and control the voltages of the network from a central point of view. Control all the generators, all the reactive power sources centrally, so that you maintain actually a good voltage profile and maintain the voltage stability margin. This is a new modern approach where we go for system wide control. The next is the coordination of protection and controls, because we have provided certain protections, so that when the suppose system is overloaded, the protections will trip the equipment, right. Therefore, tripping of equipment to prevent an overload condition should be the last resort. Now, in the sense that suppose system is operating and there is a transmission line which is overloaded, right, the protection system will look at the overloading and may trip the line. But this should be considered as a last resort, that is your protection, particularly the tripping or protection system. Wherever possible, adequate control measures, automatic or manual, controls may be automatic or manual, should be provided for relieving the overload condition before isolating the equipment from the system. This point is very important here. Idea is that here is a system which is operating. Let us say overloading takes place. The protection system will try to look at the overloading and trip the line. Our interest is that we should try to relieve the overload by tripping some loads before tripping the generator or transmission line or so on. that is the equipment. Before isolating the equipment, here the equipment means basically the generator, transformer and transmission lines. This is what is the meaning of coordination of protection and controls. Next, about the control of tape changers, but this is also playing very important role. Tape changers can be controlled either locally or centrally, so as to reduce the risk of voltage collapse. In fact, what happens is that under certain situation, the operation of tape changer is helpful. Under other operating condition of situation, right, the tape changer will not be in a position to increase the voltage, but that is going to reduce the voltage on the contrary. That is, when you try to increase the voltage, the reactive power flow increases, voltage drops, right. Therefore, idea here is that where the tape changing is detrimental, a simple method is to block the tape changing when the source side voltage sags and unlock when the voltage recovers, right. That is again actually a very centralized control we have to. There is also a potential for the application of microprocessor based ULTC control strategies. Such strategies need to be developed based on the knowledge of the load and distribution system characteristic. That is, here microprocessor based means basically it is going to be an intelligent type of control systems, right. The next step which I have discussed was the under voltage load shedding. Now, to cater to unplanned or extreme situations, it may be necessary to use under voltage load shedding schemes. The load shedding provides a low cost means of preventing widespread system collapse, in the sense that before the system collapses, right, it is better to do some load shedding and relieve the system from the overloading. The main cause of the collapse is again the overloading, more reactive power demand than what can be supplied, and therefore, if you reduce some of the loads or you disconnect some of the non-critical loads, right, then one can save the system. This approach is also used actually even for our improving the angle stability of the system under voltage load shedding. Then we talk about the system operating measures. What measures can be adopted so that when we operate the system, right, the system will not go into voltage collapse phenomena. The approach is very simple. You operate the system so that it has a sufficient stability margin. It means right now at the operating stage you design that yes, loading should not go above a particular limit, so that you have sufficient voltage stability margin. This point is also very important, is called spinning reserve. Spinning reserve, the concept is the generators are the reactive power sources, right, and this reactive power can be obtained quickly by regulating the excitation, right, and therefore, what is said is that you should operate initially the system so that other reactive power sources are used and the reactive power capability of the generator is kept reserved, because you have various reactive power sources like shunt capacitors, synchronous condensers, maybe SVC, maybe STATCOM and so on, right. Use them first and they load the generator, so that generator is operating at nearly very unity power factor condition, it supplies the real power, so that it has a reactive power capability, and use this reactive power capability to save the system from voltage collapse. That is actually the right at the design stage. Next is operator's action. Idea here is that these are the two which you can plan at the operating stage when you operate your system. Next is the operator's action, operator's intervention, how the operator can actually monitor the system, look at the complete system as a whole and take necessary action. I will talk about the operator's actions that in more detail. The operators must be able to recognize voltage stability related symptoms and take appropriate remedial action such as voltage and power transfer controls and possibly a last resort load curtailment. This is the most onerous task which is put on the operator. That is, the operator should be in a position to recognize the voltage stability related symptoms, right. So, that this operator will take remedial action before the voltage instability occurs. It means the operator has to be well trained and he can find out that yes, there is a possibility of voltage instability which may take place, and therefore, he takes certain measures and he should have certain authority to take those measures. Of course, the last resort is the load curtailment. If he feels that yes, without load curtailment the system cannot be saved, he should have the authority to do the load curtailment, and he should have that type of experience and training, so that he can make out actually that yes, at this operating condition system is vulnerable, is prone to voltage instability, and he should know that what remedial measures to be taken to save the system. A very difficult task, and that is why actually we require a highly trained personnel to operate the system. Operating strategy that prevent voltage collapse need to be established. In the sense here the meaning of this is operating strategies that prevent voltage collapse need to be established. Right at the beginning, when you are operating your system, you have to establish that what should be the strategies, so that if this happens, this measure should be taken, that should be available to the operator. And online monitoring and analysis to identify potential voltage stability problems and possible remedial measures should be invaluable in this regard. All this online monitoring. With this, I have completed the discussion on voltage stability. What we have discussed in the voltage stability, how to analyze the dynamic stability problem. This is done by complete time domain simulation. Then one can apply the certain tools, static tools to analyze the voltage instability problem. We have seen the VQ sensitivity analysis, we have also seen the QV model QV analysis. I have also discussed the continuation load flow for solids. At the end, we have discussed the various measures that can be taken to prevent the voltage collapse in the system. Thank you very much.